research, which is between complexity and crypto coding theory. And he's an expert on many things, and he's one of the people who invented PCPs of proximity, called IOPs these days, not PCPs of proximity. Interactive.
Yeah. I would have liked to.
Interactive PCPs of proximity, that today are called IOPs, I guess. And okay.
Thanks, Siri. So great to be here again. I'll be talking today about sort of a line of work that I've been really interested in and I'm really excited about in recent years. So it's been a while now. It's about efficient batch verification. I'll try to explain what that means. And it's based on quite a few works. I'm going to try to focus on mainly on two very recent ones. So these are joint works. One is with Nir Bitansky, Chitam Kamas, Omer Paneth, and Prashant Vasudevan, and another with Chanrui Mu, a former student, Shafiq Nassar, and also with Prashant. Okay, so kind of just to kind of recap or see what area we're talking about. So we're going to be talking about sort of interactive proofs based on this sort of seminal notion by Goldwasser, Mikhaili, and Repov. And the setting that we have, we have a prover P, we have a verifier, and the prover is trying to convince the verifier of a computational statement, which we usually formulate as does an input X belong to a language F. That's kind of the classical notion of an interactive proof, and you probably all, right, so they interact. And you probably all know that, we want, if the statement is true, we want the verifier to accept. If the statement is false, and no matter what the cheating prover does, we want the verifier, at least with high probability, to reject. So that's kind of the classical notion of an interactive proof. That's good enough for the 80s, 90s. But nowadays, often we're interested not in sort of just solving one problem, but we want to solve a lot of problems at the same time. So this kind of brings the question of batch verification. So the setting that I want to talk about today, we have case statements that we're interested in being convinced of, improving. Let's say they're NP statements, and they can be related or unrelated, I don't really care. And I'm allowed to interact with an untrusted prover who actually knows the witnesses and is trying to convince me that statements are correct. So the immediate solution is, just send over the witnesses. Everyone's happy. Send over the K witnesses, everyone's happy. And what I'd like to do today, to discuss today, is the question of can we do better? So if you like, think of it like as a direct product for proofs. So actually, let's, I think throughout this talk, have in the back of our mind a concrete, motivating question, which is much more kind of specific, but it kind of gives the feeling of what we're talking about. So let's suppose that we're given, this is a specific computational problem. I give you K integers, N1 up to Nk, and I want to verify that all of them are well formulated in the sense that they are products of two equal length primes. I want to prove to you that this is the case for all the K integers. The obvious solution, as we just discussed, just send over the K factorizations. And what I want to ask is, can I do better? Right? So the setting is I have a prover who knows the K factorizations. I have a verifier that knows the integers. And the question I'm asking, can the prover convince the verifier that all K of them are of this form, using better than K times M is the length of each prime, so K times M communication. Okay, that's the kind of basic question. Yeah. So kind of just to have the question well defined, this is our setup, right? We're talking about not just, we have the motivating example, but we think of it more generally. We have a prover who knows the K inputs and has the K witnesses. We have a verifier that knows the inputs. Completeness and soundness are sort of as you expect. Notice that for soundness, it's enough that even one of the problems is false. One of the Xi's is not in the language, then I want soundness to apply and for the verifier to reject. One thing I want to sort of really emphasize is that there is another beautiful line of work that studies the same question, but when the notion of soundness is relaxed to be computational soundness. So in the other line of work, the requirement is not that for no matter what a cheating prover might do, you want the verifier to reject, but rather only efficient strategies should make the verifier reject. This is known as computational soundness. Usually you also need assumptions there, whereas today we're going to be almost exclusively without assumptions. So if you've heard of there are buzzwords like bars and stuff like that, that is sort of in that other line of work. Here we're talking about proofs, statistically sound proofs. Any questions? Okay. Good. So I want to describe to you a trivial solution, and then we'll try to criticize it. So here's a trivial solution to our problem. So notice that I have my K problems and I want to solve them. If I was just measuring the amount of space needed to solve these K problems, then it's trivial, right? Just solve the first problem, then reuse the space, solve the second problem, and so on. You just need the space needed to solve a single problem. And if you're very precise, you also need to keep a counter saying what index you are. So you can solve it in this much space. And amazingly or luckily enough, we have this amazing IP equals P space theorem, which tells us that any bounded space computation, you have an interactive proof with the corresponding sort of verification complexity or communication. So if you just plug in IP equals P space out of the box, you get a batch verification protocol with like polynomial in that amount of space time verifier. So problem solved, and we can have a short talk today. Okay, so actually this solution sucks. Or rather, I want to point out two ways in which I don't like it and in which we'll try to improve it. Okay. So the first point I want to make is that the honest prover was like genuinely trying to convince me that my K numbers are prime products. If I apply the IP equals P space solution, it's going to run an exponential time. It doesn't help that it knows the factorizations ahead of time. If you just go ahead and run the IP equals P space solution, it will run an exponential time. It's solving a P space complete problem. So that kind of what I would like is to have what's known as a doubly efficient interactive proof, which just means that the honest prover should run in polynomial time given the witnesses. Right? If it knows the factorization, for example, in our concrete example, it should run in polynomial time. So I'm looking for a doubly efficient solution, which the IP equals P space theorem does not give me. The second point of criticism is that if you apply the IP equals P space theorem, the verifier actually learns highly non-trivial information about the problem. Okay, particularly, it's going to have a very hard time simulating this type of interaction. It's very likely not zero knowledge, this kind of solution. And especially if you think of the situation, the reason you're looking at prime products is probably related to RSA. It's like secret information. You would like to have good guarantees. So the second problem that we're going to focus on, can we have actually a zero knowledge proof, a zero knowledge batch verification proof? And here we're going to talk about it in the second part of the talk. We want things to be sort of unconditional. So we'll see it later on. So these are kind of my main points of criticism to just plugging in IP equals P space, and we'll try to see what we can get without it. Questions? Okay, stop me anytime if you have questions. Oops. Yeah, so I want to first focus on the first aspect, doubly efficient proof, and then we'll talk about the second. Yeah.
Maybe just to give parameters clear.
Yeah.
So M times K would be the trivial bound.
For communication.
Right. And running IP equals P space would give what bound?
So I mainly care about the dependence on K.
Okay,
You
so
get
it's
like polylog K. Yeah. And actually I have it here. So completeness and soundness, as we said before, we're aiming for communication to be much better than K times M. Ideally, we would like it to be something like M times polylog K. I should mention that I was planning to mention later on, but I'll say it now. Due to works by Goldreich and Hastad and the work by Goldreich and Avi and Cyril Wadhan, we know that the M factor should be there. We don't expect to solve even a single instance with better than M communication. But now we're solving a lot of them. The question is more about K. What's the dependence on K? So we want ideally something like M plus polylog K we'd be very happy with. And going back to the double efficient aspect, we want the honest guy to be efficient. Okay.
Did you say M plus or M times?
I would prefer M plus.
Whatever you would like.
I would like 1 times M plus log K would be my dream. That's an open question. Yeah, so question?
Yeah, so we don't care about the specific problem or the specific way the witnesses are.
I would like to have the general results. For example, for the specific prime product, it's a motivating example, but the only way I know how to solve it is via a generic protocol. I think I'd be sort of interested, but then also disappointed to learn of a specific protocol for the problem. But I think that it's what can you do for NP? What can you do for large classes? But it is sort of, I think, there's motivation to study for concrete examples. I'm thinking of it sort of more generically.
If you did for one NP-complete problem, wouldn't you get the solution for all of them?
Yes. I mean, you need to be careful what is the cost of the reduction, but basically, yes. Okay. So what's the state of the art? Well, in the sequence of works, the first one I actually talked about a few, I guess, 8-ish years ago here. It's a series of a lot of R's. So joint works with Omer Reingold and Guy Rothblum. What we showed is that it's actually possible to do it for a very large class of NP relations. It's a class of UP relations. Just to remind you, UP is the subclass of NP relations in which when you're talking about the yes case, there's a unique accepting witness. Okay, so canonical example would be unique set, where distinguishing formulas that have exactly one satisfying assignment versus the unsatisfiable formulas. And another fun example is the prime product, right? If I give you an integer and I claim it's a prime product, if I just give you the factorization in a canonical way, then it's a unique proof. Right, so this is sort of the TLDR. Let's be a little bit more specific. So what we showed, sort of the last result with Guy in this line of work, we showed that every UP relation or UP language has an interactive proof in this batch setting for k instances. The communication is sort of what you want. So especially it's polylog k, like we wanted. There's poly m, which I'll discuss in a second. The verifier, well, first of all, poor verifier needs to read its input. So there's a k times n factor with an OTIDA, which we're fine with. So they're just reading the input. And then the rest sort of corresponds to communication. By the way, throughout n is the input length, m is the witness length, and k is the number of instances.
Is m different than n?
I think of them as polynomially related. So here I don't mind so much. And the prover is polynomial time. So just very briefly to mention about this like poly m factor there. So if your NP relation happens to be either bounded depth or bounded space, then actually the poly m can be an O tilde of m. And I mentioned before already that the m factor is inherent. There should be some linear in m dependence, which is indeed there. Okay, so this was sort of the sequence of works with Guy and Omer. We managed to get kind of what we wanted, other than the fact that it's UP. So this is, I think all of those works were pre-COVID. So I wanted today to tell you about some like newer stuff. So I won't go into the proofs of that, but rather the continuation. So let's take for granted that we have batch verification for UP and keep exploring, right? And the main like open question for me, what is this like UP thing? Why are we stuck with UP? Can we extend it to all of NP? That's what we would like to show. And it seems like the restriction to UP is because of the proof techniques. And we had a different approaches, but all of them were using UP in one way or the other. It seems to be an artifact of the constructions. And it's not as though we know that UP is sort of not easier than NP in some specific way, right? The Valent-Vazirani proof. So it seems like if we can show it, we don't know how to use their result to extend it to NP.
Maybe I'll, or you will say what it means. I mean, there's a reduction. You can take any NP problem, coloring, satisfiability, and reduce it to another one with like only one solution, unique coloring. Or unique
Right. The problem, though, the reason why it's more tricky, it's not the car production. It's not like one-to-one. You produce many instances, and that causes, and it's randomized and causes issues. That's why the proof doesn't extend automatically. But it still feels morally, we should be able, if we do it for UP, we should be able to do it for NP. And also as further evidence, we know from what we said before, that if I remove this restriction for an efficient prover, we have a solution for NP. So all the indications seem to be, we're just like not smart enough, we're stuck with these like proofs that use UP, we should be able to do better. And that was my state of mind for a long time. And I was trying really hard to extend the result to NP. The news that I have to share with you is that actually, based on a new result from this year, we have, I would call it evidence against the extension to NP, but I will leave it to your interpretation. I'll describe the result shortly. But my state of mind now is that it seems unlikely that we will be able to extend it to NP. And the reason for that is what we showed in this work, it's a joint work with the one that I mentioned with Nir and Chetan and Omer and Prashant. We showed that if you have a problem that has batch verification proof, this actually implies that the same problem has a different proof system, which has a hiding feature. And it seems to us unlikely that NP would have a similar hiding feature. So let's be, that's kind of the high level. Let's be more precise. Any questions? Yeah.
Yeah, actually, I mean, I know you said you won't get into this, but can you at least say some sentences why for UP you can get something?
Oh, the positive results, how they use it.
Yeah, because like
Yeah, it's sort of we use it to sort of tie the prover's hand. So like so you have this batch situation. Usually the hardest case is when all of them are yes instances and there's only one no instance. If you have a lot of no instances, you're subsample. But you have just one no instance. And now when you're talking about the UP, it's kind of the cheating prover for those instances, its hands are somewhat tied. It needs to either behave honestly on those guys, or if it behaves dishonestly, then you start catching it. So it limits the amount of flexibility, whereas if you have a lot of potential witnesses, your strategy could be consistent with a lot of different possibilities. That's kind of the moral intuition. Okay. Cool. So let's discuss things a bit more precisely. And I want to describe to you the specific notion of hiding that we're going to show. It's a notion that's called statistical witness indistinguishability, or SWI for short. And it's a relaxation of zero knowledge. Okay, so for the moment, you don't need to know or remember the precise definition of zero knowledge, but morally, zero knowledge or statistical zero knowledge means that in the interaction, the verifier learns nothing, basically. Whereas statistical WI means it's a weaker thing. It says the verifier doesn't learn which specific witness the prover was using. Okay? How does this materialize? Technically, it'd be a little bit precise. So by the way, the notion is due to Feige and Shamir from 1990. So we'll say that an NP relation, so an interactive proof for a relation R is statistical WI. If you look at any input X and two potential witnesses, W0 and W1, and you look at the interaction of between the guys when the prover was using witness 0, or the same interaction when it was using witness 1, if you see either this one or that one, you don't know which one happened. But in a strong statistical sense, if you look at the transcript here versus the transcript there, the statistical distance should be small. Okay, so it looks the same. In particular, the solution of just sending over the witness is problematic here unless there's only one witness. This makes sense?
It's not fully well defined, right? This P of X, W0, for example. I mean, the prover can compute W1.
No, so right, okay, so I think you're making the point. So it's crucial here that we're talking about an efficient prover. So an inefficient prover could just go throw W0 to the trash and find the lexicographically first one.
You didn't stress it. We are not talking about efficient provers only.
Yes, and I will stress it shortly though. But yeah, I totally, the definition only makes sense if you're talking about efficient honest provers. Okay, so what we show in this result is that if you have a language L that has a batch proof, there's an efficient way to prove K instances, then the same language has this SWI proof. So some other form of proof that has hiding features. Okay. There's a restriction to public coin here. Public coin means that the verifier messages are just like random coin tosses, which is like all protocols that we have in the literature in this field sort of are of this nature. And we can also get rid of the restriction by making another function of one-way function, but let's kind of not worry about that too much. So notice I have an asterisk there for the SWI. So there are actually two caveats to the result, or to the notion of SWI. First of all, the statistical error that we got, sort of the statistical distance between the two cases, we would have liked it to be negligible, but it's not. So it's inverse polynomial. So it's small, but it's not that small. That's like one caveat. And the second, when we construct this SWI proof, the honest prover there is non-uniform. So you can implement it by polynomial-sized circuits or Turing machine with advice, but it has a non-uniform feature going on. These are two caveats of the proof that we don't know how to remove. Still, I mean, especially if you think of it as kind of as a negative result, which I'll try to explain in a second, I don't mind these that much. Okay, so indeed, that my interpretation for this, which, you know, we can certainly, I think it's arguable, or okay, so this part is not arguable, right? So this is a theorem. if we manage to extend the UP result to NP, so if we show that NP has batch proofs, then we get that NP has some form of statistically hiding protocol, right? And to me, it seems unlikely that, say, the satisfiability of a general formula that may have a ton of assignments can be established in a way that does not reveal which assignment you were using, in a statistical sense, not using encryption and stuff like that.
Is there any other, I mean, is it intuition or is there other consequences of this that you?
There are none, and that's one of my key open questions. I should say that if we were able to extend this from SWI to SEK, this would collapse the polynomial hierarchy. Okay, so it feels like SWI. My feeling about SWI is that, you know, it has the trivial case of UP, but if not, then it seems to be kind of in the ballpark of SEK. And for SEK, we know that this is very likely impossible. And by the way, it seems sort of, this seems so ridiculous that we should be able to provide better evidence for this. I've thought of this for a while. I've asked other people to do it. And I think for the complexity theorists in the crowd, I think it's a great question. So give evidence that NP, it seems easy, but I wasn't able to solve it. Give evidence that NP does not have SWI proofs.
We know an oracle that shows that there are no deterministic reductions from NP.
Okay, so I will reinterpret your question as two separate ones. One is like, can you show oracle separations? And the other one is what happens if you restrict to deterministic batch proofs. We have some initial results for deterministic, ruling out deterministic batch proofs, but it's more of like, it's a non-result. You would want to say that these results would.
Deterministic, you mean the
prover. The prover takes the witnesses and sends them to the verifier.
There's no
like an NP style,
NP style.
An NP style proof.
Yeah.
Seems ridiculous. So there, even there, what we know to show is that it would imply amazing crypto. So it implies like amazing, like positive result. Right? We would like, which seems unlikely we would be able to like prove without anything. But it's, I would prefer to show that the polynomial hierarchy collapses or like something we don't believe is true. So even weak forms of this question, we don't know how to rule out. We do have some like oracle ideas for some oracle separations.
But just for the basic question of a reduction from NP to UP. We have a randomized reduction, randomized to reduction.
Yeah, so yes, there was work by Dieter and a student, I think, showing that for the isolation lemma, you need to be randomized.
Okay.
Yeah. Okay. Cool. So now I want to sort of address something that Avi said before, or so we have this basic thing. We go from batch proofs to SWI proofs. And just a second, right? We said that UP, we have all of these R guys who show that UP does have batch proofs. And I'm telling you that batch proofs imply a hiding property. So all of a sudden we get that UP has a proof with a hiding property, which seems equally unreasonable. Then we think of it a tiny bit more, we realize that we only show that batch proofs imply SWI, and UP does have SWI proofs, which are just like send the witness. This would hide which witness they use because there's only one, right? So, so meaning that the UP results actually live in harmony with the negative result and sort of explains why we were stuck at UP. Okay. The second point I want to address is what Avi brought up. We also had the trivial result from the beginning, which was via the IP equals P space, which did apply for any NP relation. So the answer already popped up. Never mind. Right, so we know that via IP equals P space, we do have a batch proof for all NP relations. So now I plug in our new theorem, we get that NP has statistical WI proofs. Right, but again, it's not an issue because it's true that NP has SWI proofs with an inefficient prover. The prover just takes the witness, throws it away, and runs an exponential time to find the first witness.
I was thinking that there should be a class under NP with SWI, everything in NP with SWI proofs.
So SWI, you should think of it as a subclass of NP. It only makes sense for NP relations because we're talking about a specific relation.
So UP is contained in it, or
yeah. So UP would be contained on SWI.
So if we don't believe that UP is equal to NP, so
you ask whether it's equal to UP.
Right, but so you know, if you SWI could, yeah, so, you know.
If SWI is equal to UP?
It's connected or.
So it seems that SWI is some like, so it contains, for example, UP. It also contains SDK, or rather SDK intersect NP. And it contains like weird like combinations, annoying combinations of those, right? So you have like half a witness from there, half a witness from there. Those are the type of things I know in SWI, just weird combinations of UP and SDK. But could very well be there are other problems that I haven't thought of. Yeah. Okay. So, so indeed, I want to emphasize when talking about SWI, we insist on an honest, polynomial time, an efficient, honest proof. Cool. So I want to show you how we do this. So again, we're talking about converting a batch proof into the statistical WI proof. And as an initial step to get there, I want to think of a further relaxation. So a notion of a distributional SWI. What do I mean by that? Or DSWI. So let's fix our NP relation and assume that it has a batch proof. And for simplicity, let's assume that the batch proof is an NP style proof. So just, you know, single shot, you take the K witnesses, you put them together, you send them, and that's the proof. No like randomness on top of that. For simplicity. So it's essentially just this compression function. It takes the input and it takes the witnesses and it outputs something short proof pi that's much shorter than K. Probably like we think of it maybe polylog K or something like that, which is convincing. What do I mean by this distributional SWI? I want to assume that there's a distribution in the background over these triplets of an input and two potential witnesses. So distribution D that we care about. And as a first step, I want to show that if I have a batching proof, then I can get SWI for inputs that come from this distribution. Let's think of this as an efficient example of a distribution for the moment. Okay. Good. So how do I do it? It's actually pretty easy. So here's the situation, right? I start off with a batch proof. I'm trying to construct this distributional SWI protocol. So it's a protocol for a single instance. I have a verifier that knows X. The prover also knows the witness. And I already told you we're going to use the batch proof, so it needs to come up somewhere. So I'm going to use F. And, you know, F will produce a proof. I will send the proof and the verifier will check it. The only question is what inputs I plug in. And I do the natural thing, right? So I'm going to, the function F has K inputs. K, each input is an input in an instance in a witness. I will throw the XW into a random location, right? So it ended up being there. And in the other locations, I will just set up like random, so I'll sample from the distribution at random and place the corresponding inputs in the other location. So all the orange guys are random samples, right? So this is the proposed protocol. And if you think of it, you know, the proof function F, someone designed it, someone claimed it has a batch proof, it was designed, and now it's getting all these inputs. All of them, all K of them are coming from the exact same distribution. It has no idea what this blue one is. So how is it? And it outputs much less than K bits of information. So how can it leak any? It's going to be like lose a lot of information about all of the witnesses, in particular about W, right? We'll see it more precisely in a second. So completeness is kind of immediate. You know, if this input was in the language, we sampled all the other ones in the language, so it follows from the batch proof. Sums is also easy, right? If the particular input we care about is a no instance, there's no witness. And the other guys, even if I plug in yes instances, the cheating prover plugs in yes instances for all of them, right? I should have said here in the proof, you also send the X's that were sampled here. Okay, I don't care that the communication is long, I only want it to be hiding. So you send the X's, one of them, we know that one of the inputs is no, so it will follow from the sums of the batch proof.
This is relevant only if M is much bigger than N, right? Otherwise, you're sending the X.
I'm sending the X's, so like the communication here will scale with K.
Yeah.
But I don't care about, for here, I don't care about communication, I only want the hiding property.
I don't care about them.
Yeah, right, because I'm reducing from the batch proof to the single instance. Yeah.
But the reduction is ice, but okay.
Yeah, yeah. So I'm not going to get a short.
But it's not, you're not using it as it's a batch verification. I mean, you're not using that the batch verification is a polylog K.
I'm using that the communication is short, but the length of the proof is short.
The length of the proof contains the X.
But this proof, right? So this part of the proof is the only part that depends on the W's, and it's going to lose information about this W.
Yeah, so it's relevant only if the W's are much longer than the X's, right?
Why?
And pi is not including the x's that are getting sent, right? There's like a separate.
Yeah, so right, so you should
pi-
think of like here I have like x's that are separate. And those if the problem is hard, they don't reveal information about the witnesses. And the pi is the only one part that does depend on the witnesses, but it's compressing. Right? Okay. So what's the intuition for SWI? Well, we said before, right? This function f is compressing. It's the part that reveals potential information about the witnesses, but everything here was symmetric, so it must lose information. And because they're all coming from the same distribution, and you can formalize it. So we use the technical lemma. It's due to del based on also. It's kind of was rediscovered in a bunch of works. It's actually it's a very clean statement. The proof is very easy, but I think it's a nice statement. So it kind of follows from Pincer's inequality. But let me first say the statement and then talk about the proof. So suppose you have a function g that's compressing. It takes k input bits and outputs much less than k output bits. And I want to consider the following two distributions, each of them parameterized by an index I. Distribution 1 is sampled like an n-bit string, k-bit string, uniformly at random, where the ith bit is fixed to 0, the other bits are random, and output, I forgot, okay, and output the g of b. Distribution 2 is do the same thing, but fix the ith bit to 1, and output g of b.
K is n?
Yes, sorry, k is n. And I realized I forgot that I added the g's there, but they shouldn't because I have them here. But basically it says that the expected distance between these two distributions over an average I is small. Okay, so there's like a double G here that have it once here and another here, so only one should only be there once. Okay. It's not hard to prove this. You analyze the K divergence and apply Pincer's inequality, but this is what it's saying. And the reason it's sort of related to our situation, you think of the proof. The prover is sort of selecting which of the two witnesses to use in every one, except for one in which it's sort of forced because it only knows one witness to put in. And this is basically saying that the expected error is going to be small. How small? Well, proportional to the amount of compression, which makes sense. Okay. Cool. So that was sort of how we get distributional SWI, but I promised you that we actually show SWI. So we work for worst case inputs. And when talking about worst case inputs, it seems quite problematic, right? Because you could think of the function f really cares about one specific input witness pair. And if it sees it, it says, that's the one I care about. I will output information about that one. And now we no longer have the distribution that I can sample from and plug it in and hide this one particular annoying one because the function was kind of maliciously designed to care about the specific one.
But you allow randomness to verify.
I allow randomness. And the main thing I will leverage is the fact that first comes the compression function. It's fixed. And now I can choose what inputs I feed into it. So if, for example, I knew that it's a compression function that is targeting one specific X and W, then in all other locations, I would put the same X and like random inputs W, random witnesses or the witnesses that it cares about. So there is some hope, but that's if I know that it's a specific one. And the question, if I have a general one, which is fixed, but I don't know what its structure, how can I try to fool it? Interestingly, we can do this. And the idea is as follows. So what we showed so far with the distribution as SWI is that for every distribution over triplets, we can find a distribution over all the other inputs that will make the proof be WI. The distribution will be just say copies from the same distribution. And it will be for reasons that will be apparent to you immediately, but if not, then in a minute, it will be convenient to represent this via two-player zero-sum game. Okay, what do I mean? So think of it as follows. There's a row player who chooses the distribution over the triplet, the distribution D. And there's a column player that chooses the distribution over the k-tuple. It's really k-1, all the other entries, whatever. And what we have showed you, and let's say that the payoff is the expected WI error.
this row and column are supposed to be meaningful, or it just?
I don't care whether it's like the fact that one's called column and row, you mean, or?
Yeah.
No, the
No, so
player
it's
one,
not
player
wrong,
two.
but it seems suggestive. So
No,
it's
sorry.
suggestive.
Sorry.
It's A and B.
A and B. And the payoff is the expected WI error. So the row player is trying to maximize this error, trying to choose like a very bad distribution on what you put. But we just showed that the column player has a strategy that will guarantee some like limit to the WI error, some bound on the WI error. Right? And so game is symmetric, so zero-sum game. What we can now do is invoke the min-max theorem, which tells us if we have such a situation, then there exists a strategy, a mixed strategy for the column player that would guarantee the same payoff no matter what strategy the row player takes. Right, so there is a fixed distribution over the k-tuples. So why is this miracle happening? Is because we fixed the function f. The function f exists. Therefore, there is a specific mixed sort of distribution over the k-tuples that guarantees the same payoff as we had here, no matter what distribution you choose over the original three-tuple triplet. Okay? Why is this helpful? Well, actually, we'd use a variant of the min-max theorem, the sparse min-max theorem, which says that moreover, right, in general, this mixed strategy could be over an exponential size domain. So it would be hard to represent. The sparse min-max theorem says that you can actually do it using a polynomial size representation, or so the support is going to be small, and now you can fix the support inside the description of the honest prover. So this would be a non-uniform advice. This makes sense?
This is Lipton-Young.
Yeah. And that's basically it. Let me just mention a few extensions. So maybe I should pause if there are questions. Okay, so let me mention some extensions. First of all, here I was assuming that it's sort of this NP style batch proof, but in general, I want to be able to handle or reason about interactive proofs. So first of all, the first extension, if you think of if you allow an AM style, so there's just randomness in the beginning by the verifier, and then you send a proof. The extension is pretty easy. You just need to be able to handle sort of randomized compression functions. So that's pretty easy. And our observation is that if you talk about an interactive protocol, but you restrict yourself to honest verifiers, then, okay, so why are they interacting? They're sort of doing this interaction for soundness. But in terms of the hiding, and when we talk about the hiding protocol, and we're talking about an honest verifier, we can sort of, without loss of generality, just think of the verifier revealing all the randomness in the beginning. Because the prover is honest, the verifier is honest. So you can just do that, and then it sort of reduces to the AM case. But that's assuming it's sort of honest verifier SWI. In order to extend also to malicious verifiers, then we observe that existing transformation that we have in the SDK literature from honest verifier to malicious verifier actually work for SWI. And in the public coin setting, they're unconditional. In private coin, you need to assume also one-way functions. Or rather, for SDK you don't, for SWI you do. Never mind that. Okay? I would also mention very briefly, notice that in our result, we didn't really sort of, in terms of the soundness analysis, when we went from batch proofs to SWI, the soundness kind of just converted. So if we had started off with computational soundness, we would end up with computational soundness. Turns out that if we apply our result to existing batch arguments that we do know to exist, so batch computationally sound proofs that do exist, we actually get non-interactive SWI, and we can actually get all the way to zero knowledge there. Okay, so this is sort of a positive result, but it's in a different regime of computational soundness. So that's the only brief thing I wanted to say about computational soundness today.
But there, maybe you care more about the error being just polynomial.
But you can, so we can reduce it there. There we can solve kind of our problems. We don't have the non-uniform honest prover. We don't have the inverse polynomial error. Like there we can solve all our problems. We have more tools at our disposal. Yeah. Okay, so that's all I wanted to say about the first problem. That the honest prover was, we wanted to be efficient. The second part of the talk, I want to talk about the fact that the proof reveals stuff. Actually, how am I doing on time?
You have 21.
Okay. Cool. So the second part of the talk, I wanted to talk about the second sort of problem with the IP equals P space theorem, which is that it's revealing stuff. And I would like a proof that's zero knowledge. Okay. So going back to our favorite example of the day, we have these k integers. We wanted to check that they're prime products. As we said previously, the problem is in UP, so we can apply this result with Guy, and we get a protocol that has sort of M polylog K communication. So we're pretty happy. But that protocol is even worse in the sense in IP equals P space, because that protocol actually explicitly reveals some of the witnesses. So it's kind of as non-hiding as you can get. And the question that I want to ask now, can we do batch verification while preserving, say, strong hiding properties like zero knowledge? Or for general, we'll see in a second. Okay, so the general question that I want to ask, okay, so in a second we'll ask the question just to remind ourselves what is statistical zero knowledge. So we have the same setup sorry, we have a verifier and a prover. The reason why we're not restricted to UP is for the moment, when talking about zero knowledge, I waive the restriction of efficient honest prover. Right, so now I'm potentially allowing the honest prover to be inefficient, but then I'm requiring the protocol to be zero knowledge, right? So what is a statistical zero knowledge proof? It's a proof that reveals nothing beyond the fact that the statement is correct. And formally, it means that for any verifier strategy, there is a simulator that outputs a similar interaction with only some like small statistical deviation. And not super important for us, the exact, but it's a strong sort of statistical notion. So I look at SDK, and I think like in the complexity crowd, I'm preaching to the choir, but it has amazing structure, right? So in general, like why study SDK? It has complete problems, it's closed under complement, it's an incredibly influential notion. And it also captures a lot of the problems, or essentially all of the problems that we care about in crypto, or at least variants thereof. So things like factoring, discrete log, lattices, and luckily enough, also our favorite problem of the day. So if you care about proving to someone that your integer is a prime product, there is a statistical zero knowledge proof for that problem, for a single instance, okay?
Use prime products in a real way, that the number is composite in a particular way.
Yeah, so you don't like the term like prime product you don't like, or?
Yeah.
Okay.
Everything is a prime product.
Sure.
Prime.
My notion of product is limited.
Anyway, it's composite.
Okay.
Two factors.
Okay. Yeah. But we understand what I mean. Product of two primes. So two prime product. Okay. So here's a question that I want to pose. Suppose you have a language that's in SDK. Does it have a batch proof? A batch proof that is itself SDK, right? And with short, so one thing you could do is just run the SDK protocol individually for each one of the K inputs. That would still be SDK. So you have a little bit of a loss from like a union bound over the K instances, but it's not too bad. My question is, can you do the same but have short communication? Okay. And sadly enough, I don't know what the answer to that question is, so it remains open. It's, I think, a really interesting question. We can show it for a subclass of SDK, which is very rich in itself, which is known as a non-interactive SDK, or NI-SDK. Okay, so it's a subclass of SDK, for which, we'll see the theorem in a second, if you have a language that is in this subclass, then the batch problem is also in this subclass. Okay, what do I mean by non-interactive SDK? So same picture as before, we have a verifier and we have a prover, but now the proof, rather than being interactive, is a one-shot thing that the prover sends to the verifier. And actually I'm cheating, you can't, this is like too good to be true, you cannot have this. So actually both parties are going to share some common randomness that is generated as like a trusted setup in the beginning. You should think of it as uniform points, uniform random points. And completeness is immediate. Soundness says that if you have an instance X that's not in the language, then with high probability over the CRS, there simply will not exist an accepting proof. And zero knowledge says, zero knowledge says that if you have an input that's in the language, there's a way to generate a distribution of like whatever the verifier saw, which is the CRS and the proof pi, you can do it without knowing the witness. You can do it by yourself. Okay. And luckily enough, so this class is large. It doesn't contain, it seems, it's debatable whether people think it's equal to SDK or not, it's open. But it's still sort of, it's known to contain a lot of our problems, including the 2' project of 2' that we had today. And so it doesn't contain all of it's not known to contain all of the problems that are in SDK, but it contains a lot of them. Questions?
Graph isomorphism.
Yeah. So graph non-isomorphism. I need to record if yeah, it should. I want to think that there's the case when it doesn't have automorphisms, which I think is definite. I think also when it has automorphisms, it's fine. But yeah. Your protocol is private coin.
Yeah.
Right. So here I have like a public randomness, so I need like the Goldwasser-Sipser and but it's right. You send the hash. Never mind. Okay. Okay. So what I want to show you is describe as the result for batch verification of non-interactive SDK, which is what we know how to achieve. In this joint work with Changuri, Shafiq, and Prashant, we showed that if you have a problem that's in NISDK, then you get a batch proof for K instances, which behaves as we would like. The proof length is polynomial in M, in single instance, and polylogarithmic in K. Okay? I should say, and I'll talk about it later on, the honest prover here is going to be inefficient. Later on, we'll partially resolve that, but let's ignore that for now. Yeah. So I want to, I don't think I'll be able to show you the main parts of the proof here, main ideas. Okay? And actually, let's focus first on warm-up. Okay? And the particular NISDK problem, which will be extremely easy to batch. It will serve as a good example. So the warm-up that I want to consider is checking permutations. So what is the problem? So I give you a circuit which maps n input bits to n output bits. And I promise to you that it's either the circuit is either a permutation, in the sense that the function is a permutation, not permutation on the bits, right? Permutation on the entire input space. And in no cases the function is 2 to 1, so it's highly non-injective or very far from being a permutation. And a non-interactive SDK protocol for this problem is the following sort of very easy. So let's think of in trying to solve a single instance of this problem in zero knowledge. What would a non-interactive SDK protocol for this problem be? Where the CRS would just be a random n-bit string, and the proof would be an inverse for this random string, right? So you send the inverse and the verifier checks that it's indeed a valid inverse. Why is this a good proof? Well, if F was indeed a permutation, then you can implement the strategy, it's fine. If F was 2 to 1, then with probability 1/2, this guy does not have an inverse. And the verifier will reject the probability 1/2. If you're unhappy with 1/2, you can repeat this experiment. Okay? And in terms of zero knowledge, what did the verifier learn? It learned the inverse of a random element. But guess what? It could have generated one itself. It would just sort of first generate the inverse and then compute function. But it has a description of the circuit. It can sort of start by sampling pi, and based on pi, generate the CRS. All right. Okay, so a single instance has a simpler proof. This makes sense so far? What about the batch problem? Right. So now the problem is as follows. They give you descriptions of F functions. All of them are n bits to n bits. And I'm asking you to check, are all of them permutations? Or is at least one of them 2 to 1? And if you think of it for 10 or less seconds, you realize that there's a very easy solution to this problem, which is just to compose all of the functions, right? So think of it, if all of them were permutations, then this composed function will still be a permutation. If at least one of them was 2 to 1, then this function will be 2 to 1 or even worse, will be very lossy. Right, so we basically have a car production from the K instances to the single instance, and the observation, so the new circuit that we generated here is much bigger, right? It does use all of the original functions, but its input and output sizes remain the same size. And the complexity of the previous protocol that we had only depended on the input and output sizes, the communication complexity. Right, so that's why we get a batch proof for this specific problem. Does this make sense? Okay, but the sad news is that this problem is probably not NISDK complete, so it's not good enough. But it turns out to not be that far from NISDK complete problems. So what was our strategy so far? Like with this problem, we had the k copies of the permutation problem, and we compressed them into one instance. This problem is not NISDK complete, so what we'll do is find a similar problem, which will be a little bit more difficult to deal with, that is NISDK complete. So once we have, like if we have our favorite language at NISDK, we'll reduce to this problem, that problem will batch, and we'll solve. Okay? So we want to switch over to that problem. The problem is a little bit annoying, so I describe an easier, simpler variant of it that suffices. The simpler variant is a simple extension of the permutation problem, which I describe the injectivity problem. So now the input, rather than being n bits to n bits, it will be n bits to m bits, where m, the output, is larger. And the question that I ask you is, it's a promise problem. So the yes case would be that the circuit is injective. The circuit should be larger, right, because n is bigger. That's the yes case. And the no case is that it's highly non-injective in the sense that it says it's L to 1, where L is can be even a large parameter. Okay, the injectivity problem clear? So it turned out that, I don't know if I have so this problem itself, I don't know how to show that it's NISDK complete, and it seems also unlikely. But if you allow also some errors here, then it is NISDK complete, and the errors are annoying, but you can deal with them. They're not too bad. Okay, so let's focus on the errorless case, like we have here. Okay, so we want to do a batch proof for the injectivity problem. Let's try, composition worked so well, let's try to compose again.
How much bigger is m than n?
Let's say 2 times, 2 or 3 times. You can kind of apply a pairwise independent hash and without loss of generality get that.
You cannot compose.
Right, so even syntactically it doesn't make sense. Right, so you had n bits, you got m bits, how do you feed them into the n bits? What's a problem? Then you think, okay, how would I solve it? You would hash. Right, so that's kind of the natural approach would be to have like steps of apply a circuit, hash, apply a circuit, hash, and so on. Okay, so that's what we try to do. Right, so I think that was already clear, but we have the input, we feed it into the circuit. So the blue area is the image of the first function. The gray area is the entire set we live in. And now we'll apply a hash to reduce it back to n bits, apply a circuit, apply a hash, and so on. So this would be the idea. And in terms of soundness, let's start off with soundness here. It totally makes sense, right? If like one of the circuits was highly compressing, it was L to 1, then you're going to lose information, and that information will never be recovered through just applying functions. At some point, you lost a lot of information, and you're super happy. Right? This makes sense? The difficulty that we encountered, and took us a little bit of time to get over, but is actually in yes case when all of the guys are injective. And the problem that comes up is, so we apply the circuit, we apply the hash, we apply the circuit. But the annoying thing that happens is this birthday paradox. The hash is going to generate quite a lot of collisions. So the resulting thing is no longer going to be injective for sure, which is a problem. Make sense? Okay. Yeah, so when we apply a random function, oh, by the way, for the moment, let's think of the hash function as being totally random and worry later on about de-randomizing it. Okay, so the hash functions that we're applying in each individual step are totally random and independent of one another for now. So we apply this totally random function from like an n-bit space, capital N is 2 to the little n. We're going to lose, a significant amount. If you think of it in the level of entropy, you're losing sort of a constant number of bits of entropy. Right? And it took us a while to we were kind of stuck with this. It took some works. We had like a kind of clever solution that used interaction and were somewhat complicated. And the problem that if you just follow this approach is that you lost sort of a constant number of bits of entropy. but you're doing this again and again and again, right? So in the beginning, you only had like n bits of entropy. You're doing this k times where k is huge. You're going to lose all your entropy, right? And so we made, in the initial works, we worked very hard to make sure you lost the entropy, you recovered it, and so on. But what we didn't realize, which in hindsight was kind of easy, is that we're actually very close to the solution. And the reason is sort of, if you're like, you see that in the beginning, you lost a bit of entropy, you lost a constant number of bits of entropy, and you fear that it will keep happening. It actually doesn't happen. You lose a lot in the beginning, but very quickly it actually stabilizes. Okay, so this is kind of the key observation here. And what you can analyze, it's not too hard, is if you're already have been reduced to a set of size S, that's like the active things that are still alive, and you now apply the random hash. If you look at the expected size of the image and you calculate it, it's a trivial calculation, you get that it's this expression, S times this factor. So when S was very large, when S was capital N, you do lose like a constant factor in the size. But you see that as S decreases, the amount that you lose decreases significantly, right? So just think of it, suppose that we are like k over 2 steps into the process. We claim that in this state, my set S will be of size about n over k. And notice that if you do like another k over 2 steps, each step that you do now, you only lose 1 minus 1 over k. So in like k over 2 additional steps, you're actually only losing a constant number of bits in entropy. I hope that discussion about entropy makes sense. Right, so it's actually, this trend does not continue. It happens in the beginning, but it very quickly stabilizes. Cool. So if you do the analysis carefully, you see that in the yes case, it sort of stabilizes after k steps to an image of size n over k. Whereas in the no case, we had this like single step in which we compressed by a factor L. And it turns out that this injectivity thing is NICK complete or hard, even when L is very large. So this is sort of good enough in terms of getting a gap. The difficulty though is that just looking at the image size is not NICK complete. It's NP complete. It's not good for us. Still, it's kind of close enough. So instead of looking at image size, we look at entropy. Okay. And this, this is beautiful work by Godrich, Sai, and Vadhan, or first there was Godrich, Vadhan, showed that, if you look at Shannon entropy, for example, computing the Shannon entropy sort of characterizes is complete for SDK, and there's a variant for NSDK. So we started working with it. Shannon entropy turned out to be problematic for a lot of reasons. What we ended up working with, I'll try to explain briefly why, is that if instead of looking at Shannon entropy, you look at Renyi entropy, like everything works out beautifully. So just to remind you, Renyi entropy is kind of the log of 1 over the collision probability, which kind of think of it as like proportional to the collision probability, where collision probability of distribution is just, you take the distribution and sample twice, and that's what's the probability of getting a hit. Okay, or it's proportional to the L2 norm of the description of the distribution. Okay, so Irit, how am I doing on time? Like 5-ish or 10-ish minutes?
You're almost out of time.
Okay, sorry.
Another 5 minutes.
Sorry. So let's, so sort of you can extend the same analysis that we did for the image size. You can do, it's a little bit more complicated. You can do it also for the Renyi entropy. So let me skip that. So you kind of compute the expectation and variance. It's not too hard. The last thing I will try to say is, and basically what you get is like distinguishing between having high Renyi entropy. So you'll get a gap between, like, in the yes case, you have a lot high Renyi entropy. In the no case, you have a small image size. And that's NICK complete. The only thing I say briefly is about de-randomization, because we were assuming random hash function throughout. So if you look at the analysis with the Renyi entropy, it's not, the analysis kind of immediately shows that it's enough that each individual hash function will be 4-wise independent, and the analysis still goes through. Kind of, you need 4 because you have, you need pairwise, but you're analyzing variance, so you need twice the pairwise. So this is fine. You know, if we replace each hash function by 4y's independent hash function, it's fine. But still we run into a problem because we have the k of these hash functions, and we would like them to be independent for the analysis because it's like a gradual process. So if we just follow this approach, we would have a short proof, but a very long CRS, proportional to k. So we do something more generic. So what we do is we observe that computing the Renyi entropy or the collision probability is actually a bounded space process. Right? So you're thinking of the function that just like looks at the description of the k 4y's independent hash functions, and you're trying to compute the collision probability. So you only sort of need to remember where you are in the process. So overall, this entire thing is a bounded space computation. You can de-randomize it using a Nissan's generator for read-once branching programs. So this is yet again another place in which we were using specifically the fact that we were working with Renyi entropy. Because with Shannon entropy, I don't know how to de-randomize it similarly. Maybe with expanders, it would probably more complicated. Okay. So just to summarize, what we did was we composed the injective functions with the random hashing. We intertwined them, sort of. The collision probability, we just said, can be computed by a bounded space algorithm, and therefore can be de-randomized by NOM's PRG. Okay. So very briefly, because I'm out of time. What we showed in the first part of the talk was a doubly efficient batching proof for UP. In the second part, we saw an SDK batching protocol. The point I want to make is that the first result, sort of, which I didn't show you, the positive result for UP, the protocol is very not ZK. And the second protocol, the protocol is very not doubly efficient because it requires inverting, right? Even for the permutation example, it requires inverting the permutation. So we have like two protocols, each of them solves one of our problems, but not the other. And it would be nice to have a single protocol that does both. So in a very recent work that my student, so it's with my student Or Carrot and with Prashant, we actually showed that you can combine these two proofs, which are really, it's kind of surprising at first glance because you can't really use either one of them because they both have like significant caveats that you don't want, but you can actually compose them and get sort of the best of both worlds. But this requires interaction. Let me skip this. Cool. So I guess I think this entire area of batch verification, we started with it as a sort of technical tool in 2016 towards getting something else. But as I've been studying it more and more, I think there's a lot to be done here. And it's been a lot of fun working on it. So I want to encourage people to look at it. I'm sure that's possible to do double efficient for UP. We can do it for the subclass of SDK. And we have this negative evidence for NP, we discussed in the first part of the talk. So just to conclude with open problems, I think we said most of them during the talk. I think more compelling evidence against NP batching would be extremely valuable. And it seems, you know, in particular, can we rule out statistical WI for NP? Seems very plausible and should be able to say something, but I have not been able to. This question of batching interactive SDK, which I don't know how to solve. And then I think Irit or maybe someone else raised it, you know, the positive results that we have always have this polylogarithm multiplicative factor. Can you reduce it to a constant overhead, even maybe 1 plus or additive overhead? That would be amazing. And in general, sort of understanding, we have these sort of like, in terms of positive results, we have results for UP, we have results for SDK or subclasses of SDK. It would be nice to characterize what problems admit efficient batch proofs. Okay, so way over time, so let's stop here. I'm happy to take any more questions.
So do you think the approach for non-interactive SDK should somehow extend to the?
I would like to think so. So Salil has like most of his later works on SDK typically sort of analyze the NISDK case and then extend to SDK. So morally, we feel that we're following these gigantic footsteps, and we tried. So there is some form of reduction, not the carp reduction, but some other form of reduction from NISDK to SDK, but it's not suitable. But Salil usually uses that trick. So I want to say yes, but I've tried it and I failed, so I'm not sure what to say anymore.
Last time that happened, you failed.
Right, for a reason.
Send UP to NP.
Right. Yeah, yeah.
It's possible that you can prove a stronger negative result, namely that batching for NP implies zero knowledge for NP.
That's unlikely because we have a positive result for UP. Right? So you think like maybe you can target a stronger hiding notion, but it has to live with the fact that we have a positive result for UP. Yeah.
Okay, great. Thank you so much.